Okay. And then I'm just gonna hide this for now. Okay, so hopefully everyone can see this is our Rockefeller BRC GitHub webpage. Okay, and this is our hub for all of our training. And so, as I mentioned before, it gives you an introduction of who we are and how you can contact us. I also said there's the YouTube channel here, so you can go here if you want. And it's going to be me, but we also have lots of recorded sessions that we've run in the past, like this RNA-seq workshop we ran in January. And so I'm going to try and get this uploaded by the end of the week up there as well. So if you want to review what we do today, you can go with that. And then as far as the actual course material, so the slides, the code, everything you need to do to run and rerun this, we have our full list of courses here. So we have a lot. We haven't got videos of everything, but we've got videos of most things at this point. But we do make updates to all these courses on a regular basis. So this is the most up-to-date version of all the courses. And so for the most recent course, we might not have an accompanying video for it. It depends. But what we're going to be covering today is Introduction to R. And specifically, we're going to be covering the abridged version, okay? And so what we've decided based on feedback in the past is we have a very exhaustive course introducing people to R, but it is 6 hours long. And so we've opted to try and do something a little bit shorter, get to the core essentials, hopefully hook people in and get them interested. And then as you develop with your R skills, you can go back and revisit maybe the longer course. And as we go, I'll try and highlight what we're missing and why maybe they're less important when you're first getting started. Okay, so as hopefully all of you have installed R and have R Studio at this point, you would have made your way to this page. It has the setup instructions. It's exactly the same for all the other courses we run. So this is, in theory, the simplest. But say you want to get into RNA-seq, you're going to be installing all these RNA-seq specific packages. And so this step can take a little bit longer and be a bit more nuanced. We also have validation checks up here. If it's green, that means our most recent version of our code is working on the most up-to-date version of R. Okay, so we try and make sure all our code is double-checked systematically prior to running the course. Okay, and that is in a way that we don't have to go through and check every single line. It's being checked automatically. While we're on this page, there's also some other parts. We're going to be, if you want to look at the slides, there's some navigation options up here, so you can look directly at the slides. We're going to have 2 parts to today's session. There's also exercises with solutions and exercises as they are. And there's the getting help. Okay, so say 2 weeks from now, you're doing some of this again, revising it, you find either you find a mistake or you find something that's just like you get an error message and you can't figure out why. You can go to here, you can create a new issue on our GitHub, and then I monitor this. So I get a notification every time something like this comes up. So you can say, I am having problems installing, if I can spell, okay? But you can then give me some details. I am on a Mac, for example, or something like that, some operating system information, and then you submit this as a new issue, okay? Then if I go back to issues, it's here. And if someone else has had an issue and they've had the same issue, it's going to be saved there as well. So you'll be able to see what other people have had problems with, and maybe it's the same thing, and you don't even have to ask me anything. It's just the answer is that. Okay. So that is getting help. Cool. So I think we've covered like most of the like admin stuff, and so we can actually start to talk about R. Okay. Oh, and this is looking funky, but that's okay. So what we're going to be covering today, in this first session, we have the setup for today. There's 2 sessions. I'm going to try and keep them to just under an hour, and then we'll have a little break. We'll have a chance for some exercises. I'll be able to run through those exercises with you. Yeah, hopefully we'll cover everything about the basic data types in R, how you interact basically in R. Then we'll get into the kind of more nuanced stuff about like bringing data into R, how you manipulate that data, and then how you export it or create plots, okay? But in this first session, it's going to be mostly focused on what is R, and then what are the data types in R, because you need to have a fundamental understanding of what data types you have to be able to to be able to understand which is most relevant for you and how best to use it. Okay, and so as I mentioned, this is the abridged version. The full version is you can go back to our home page, or you can just click on this link and it will take you there. And throughout this, again, I will try and point to maybe the relevant sections where we've maybe dropped something, but you can go and look at that to get some more details. Okay, so for setup, everyone hopefully has downloaded the course materials as well as installed R in RStudio. There's a nice link here for the download zip. Okay, and this is more important in the second session. But if you ever want to review the material, it has all the slides and information within it. So I can show you that if I go to Finder. So I downloaded it to here, I unzipped it, and within it, there is several folders. If you go to our course, we have presentations, and this contains the HTML slides, which I'm going from now. We also have single page versions. Often if someone is working through this by themselves, they prefer a single page. So it looks more like this. So it runs through. There's also just the R code itself and exercises and things like that. Okay, so once you do that download, you have everything you need to be able to just do this at home. You don't need Wi-Fi, you don't need anything. Okay, so a little bit of history on R and why we like it to start us off before we get coding. So R was created by these 2 guys, Robert Gentleman and Ross Ayaka, I think. I don't know how to pronounce his last name. But it's a language for coding that's specifically designed for statistics, okay? And so that's why it's so prevalent in academia, is because we're all about the statistics, and why it has so much strength and popularity maybe versus Python, which is probably the other main language that people use. Because Python wasn't built for statistics. It has some very good statistical operations, amongst other, like a bunch of other things, but it wasn't necessarily built from the ground up for this purpose. And so R was very imaginatively built off of the basis of a previous language called S. It was done at Bell Labs, so that's just across in New Jersey, near here. And it's really focusing on its several kind of clear objectives. You want to be able to do this kind of higher level analysis. You want to be able to have cross-platform. So if someone's over on Windows and someone's on a Mac, someone's on a server running Unix, you want to be able to use the same language for all of them and for it to be working exactly the same way. One of the other massive plus points about R is its graphing capabilities and its graphical outputs. Be that just if you want to make a bar plot, it's very easy to make it look nice. Or if you want to do some kind of 3D rendering of some molecular structure, that's also very feasible within R, and it's maybe more challenging in other softwares. And then where I think R really comes into its own is the community around R. And this community produces and makes a ton of really good packages that are very thoroughly documented. There's a whole review system that goes into making sure these packages are good enough and have enough support. And so this creates a culture of like, if someone needs something, they'll create it themselves, but then be able to share it with everyone else. And it's a very standardized approach. And so that enables it much easier for you to expand your R capabilities. And so even though we're talking about expanding our capabilities, there's also just a lot built into R, okay? And so this is this kind of out-of-the-box capabilities. What we're talking about here is something called base. And so base R is what you have installed. It's what you get when you install just R. And that has a ton of the statistical things that you already want, okay? And then there's these other repositories that have additional packages, things like CRAN, MRAN, which is the Microsoft specific version of CRAN, essentially, RForge. And what we love the most, which was also set up by Robert Gentleman, who created R, is Bioconductor. And so this is a whole suite of packages specifically for bioinformatics. There's tons of stuff on there. It's, again, a really great community. And there's lots of like information online for when you start to work on a pipeline, work on a data analysis workflow, you can actually go and see how this works, because someone's going to have made a little report or a how to use this. And it's the other part to drive home here is R is growing, okay, and it's predominantly in academia, but also in specific fields and industry as well. It's really not disappearing, even though Python's becoming like bigger and bigger. R is also growing at like a rapid rate as well. And I know this plot's a bit old, but it keeps going. So something hopefully everyone has managed to get R at this point from the R website. A question sometimes we get is, I've installed R, I've installed RStudio, what's really the difference between the two? Okay, and so R is the actual program that is going to be running things, it's going to be handling these computations. RStudio just sits on top and makes it look nice, makes it user-friendly. It's called an integrated development environment. And so once we get to this, when we do it, we're going to quickly look at what RStudio looks like. You will be able to see R within it. Okay, so if I quickly switch to my RStudio, here in the bottom left-hand corner, we have R. Okay, this is what R looks like. And if you were to open it up in terminal or command line, you would just get this little blinking cursor, and you'll be able to run R at that point. I can type things into it. I can do basic math, right? Ooh, not 1 plus exclamation. Oh God, that's good stuff. Okay, 1 plus. Oh God. Sorry, I can't see down there. There we go. 1 plus 1, 2. So I'm working in R here. Okay. Up here we also have the scripting panel. Okay. So if you're writing your own scripts or you want to keep notes as you interact with what you're doing, you can use this panel up here. It also allows you to do things like, if I want to do find and replace, things like that, as your scripts get longer. I can also open up existing scripts. So what I have done here is opened up the R script for this session. Okay, and this contains all the R code within it. Okay, so some people like to have the code uploaded or in this screen, so it makes it easier to copy and paste, because quite often that's the easiest way to do R, right? Or to do any kind of coding is copying and pasting and then thinking about it and then breaking it apart. And so you can just load this in by just doing file, open file, and then you can navigate to wherever you downloaded the course material, navigate into our course, go into presentations, and then go into the code section. Okay. The other panel here is your environment. And so we're going to start talking about variables soon. And as we create variables, they're going to be stored in here. Okay. That will make much more sense once we know what a variable is. But anything you're basically storing within R will be up here in your environment. You also have your history, amongst other things as well. So if you do a command, you want to run that again, or you want to run it again but make some changes, you can go back, look at your history, fix it, and then go from there. And then the final section we have is files, plots, packages, and a bunch of other, this is kind of miscellaneous. The main thing here is it shows you where your working directory is. This is where R thinks it is. So at the moment, mine is in desktop, but we'll show you how to move that around. And it allows you to interact with your file system. Plots will appear here, and the other big one is help. Okay, so if you're trying to run a function, you don't understand how it works, you can go to this panel and try and get more information. Okay, so that is RStudio and R. So we're actually going to start covering the kind of course content at this point. So what we'll start with is using R, how you use it for just doing some simple calculations, arithmetic, and things like that. Then we'll start to talk about variables. We'll get into vectors. One data type we won't cover is matrices. I'll explain why later, mostly because of time, but why they're maybe the least interesting, at least in my view. Data frames and then lists, okay? And so as I just showed you, I won't try and type 1 + 1 again, because apparently I can't, but at its most basic, R can be used as a calculator. You can just type in whatever numbers you want, do plus, minus, times, whatever, and it will evaluate it for you, okay? But beyond, on top of that, it has some more nuanced and complex operations within it. And so here you can see we have something that's doing the square root, okay? And so it has built-in mathematical operations that may be a bit more nuanced than just doing a simple addition. And so this is our first kind of view into what a function is, okay? And so all the function is it's something that does something to something else, typically. And the way it's kind of delineated is you'll have the name of the function, then you'll have parentheses, and then within that, you'll put an argument of some kind, or multiple arguments separated by a comma. And so here are kind of some examples of some very simple arguments. They are simple functions with several arguments within each of them. And we have min, sum, and max. Okay, and so most of the functions are designed to have names which kind of give you an idea of what they're doing. You can create your own functions as well, and it's really good practice to be very intuitive with what you're doing. But so if you use the min function, it's going to take your arguments of 2, 4, and 6, and it's going to return to you whatever is the smallest value. It's looking for the minimum. And so here you can see it's responded with the 2. We also have sum and max. So sum is just adding them up, and then max is looking for the maximum of the 3. Okay. And so this is an example of something that's a built-in function. Again, you can load in functions from other places using installing packages, or you can create your own. Okay, but most of your statistical needs will be fulfilled if you're just doing some basic statistics with whatever comes with R. Now, I hinted at the fact that you might want to get some help with a specific function. And so you can use the help in the bottom right pane of your RStudio, or you can use the question mark. So if I do this and square root, now it automatically takes me to where I can get help with square root. And so typically it will have some kind of description of what this function or a group of functions are doing. What are the expected arguments? So in this case, it's grouped together. There's kind of miscellaneous mathematical functions. So it's going to be talking about absolute and square root. And the single argument is going to be a numeric, okay, that it expects. And then typically at the end, you have some examples, okay? And so you can also just do the same right here, right? So I can look for min, and it will tell me about min and maxima and how to use them. So that's always your first port of call when you need some help. Is use the question mark, use your help pane. Normally you can solve most of your problems by looking through the examples, looking at your arguments and doing some cross-referencing. Most of the time when you have a function, the arguments won't be as simple though as min and max, where you just give it a bunch of numbers. Okay, there's typically orders that go with them. They might have several different classes of arguments that are coming in. And so for those, it's the help pages become even more important. Okay, so we're going to talk about specifically the dir function. And so what dir does is it tells you what's in your directory. Okay, so it lists file in the directory. And so you can see here the full list of arguments. So it's quite complicated, and there's an order. Okay, and they all have names. So the first one is its path, then pattern, etc., etc. So this is where it becomes important to be looking at the help page and cross-referencing when you start to use your own functions to be able to understand what they're going to be doing. Okay, but I can show you it if I evaluate it. You can also provide it with nothing, and it will still work. And so you can see here, it has defaults. And so the path, it defaults to just a full stop, which means it's going to look wherever it is right now. The pattern, it's just going to not look for a pattern. And so if I do that, it's going to return to me and tell me all the files and directories that are associated with this specific place. So at the moment, like I said, I'm in my desktop. I have my desktop essentially folder open within R. And so that's what I can see on my desktop. And so if you want to provide an argument to your function, you need to either use its name or get its order correct. So in this case, I want to use full names equals true. Okay. Now, if we remember when we were looking at the help page, the path is the first argument. Okay. So if I just provided just the argument true, it's going to assume the first argument is going to be what you provided to it, which is true, which won't be a path to anyone. Okay, it doesn't tell you where to go on any of your computer. It's just saying true. And so if you just put directory true, it will give you nothing. Okay, so you have to provide a name to your arguments. And I think especially when you're starting, it's really good, like when you're learning the functions, to just give the name every time for whatever argument you're providing. Okay, but for everything that isn't named, it's just assuming everything is default. So when I say directory full names equals true, this is equivalent to this. It's providing the path, it's looking at a pattern, and there's something else, and then it's got this final one here. And that's because full names equals true is the fourth argument. Let's check here. So this one is the fourth argument. So everything else before it is taking its default, and everything else afterwards. Cool. So it's just important to pay attention to your arguments. Most of the time, when I get an error, it's because I haven't set up my arguments right for my function. Okay, and so you can use it in collaboration with your help, then make sure you've got everything correct. Okay, variables. So everything you store within R is a variable. Okay, and so you can assign different things into these kind of placeholders, which are variables. And you do that with this little arrow guy. Okay, so it's just like the less than sign and then a hyphen. And what that's doing is it's saying, I want to put this, whatever this thing is, in this case, I want to put the number 10, and I want to store it as X. Okay, and so then when I type X into the computer or into your R console, it's going to return what's contained within that variable. And so it's going to return the value of 10 here. Okay, so I can show you that in action. So we can store, we'll do 12 this time, and then X. And so now you can also see in your environment, there's been an update. You now have a variable. The variable is X, and it contains within it 12. Okay? So everything you do in R is pretty much going to be creating variables, modifying variables. Anything you want to persist for any length of time, you're going to need to use a variable to do that. And so often you're going to be making updates to variables. And so basically every time you assign to something, you're overwriting. And so in this case, we remember X is 10. But if I now assign something new to X, that 10 is gone, and it's now this new value, which is 20. Okay, so every time you're making a modification, you're completely wiping it. So there's something to be careful when you start to do like lots of manipulations and working with your data sets. You can easily accidentally overwrite your data that may have taken several hours to process just by using the wrong name or getting a little bit confused. Okay. And then once it is a variable, you can then use it in operations. And so that arithmetic and math we talked about earlier starts to get a little bit more complicated because we're using X now as whatever is inside X. And so it's, if we remember, it's 20, and we're going to do X plus the square root of 25, and that's 20 plus 5, so that's 25 again. Okay, so you can see how we can start to build these things up, get more complicated pretty quickly. And so we can then assign this output, right? All we've done right here is basically create the value 25. And so we can then assign that to a new variable. So we're creating a new variable, which is y. Okay, so y is being assigned to it, X plus the square root of 25. Yeah, what's up? Pardon, I didn't hear that. Yeah. Oh, okay, yeah. So this is your output. So so let me go to my screen now. I'm going to copy this. So you can see here, and then we just do y. You get a one back. And that one is just saying this is kind of, it gives you like, as we get further down, you'll start to see variables that have multiple entries. So things like vectors, data frames, and lists. And these numbers give you like some clues as to how big they are. Yeah. You'll see as we get there, but yeah. This is essentially, it's just part of the output of R. Okay, so now we've talked about variables and we've talked about like individual numbers and things like that. We want to actually build something a little bit more complicated. We don't want to just use single digits, right? And so we get to our first kind of proper data type, and that is a vector. And so people, like a lot of these data types are going to be quite consistent, and you'll maybe recognize them if you've used other programming languages, or even just math, because a lot of the names kind of transfer across. But vectors, even though it's maybe the most simple, is one of the ones we still use the most. And all it is like a one-dimensional collection of things. Okay, variables of some kind, numbers, characters, whatever it may be. And so even when we create a variable and it's 20 and it's X, that is still a vector at that point. It's a vector that is of length 1. Okay, and we can check that by using the length function. We can always ask the length of something, and it will return, in this case, the number 1. Okay, because it has one number in it, and so that's how long it is. But if we want to create something a bit longer, we have to use the combine function. So this is a simple C, and then it's whatever you want to be in your vector, separated by commas. Okay, so in this case, we have 1 through 10 just written out. And if we assign this to x, now contained within x is 1 through 10. Okay, so we can see this on okay, and so we have our x here. Okay, and so we can also now do length of this one. And you can see it has 10 entries within it. Okay, so we've created a vector, it has 10 different positions within it, and you can measure its length very easily with different functions. There's also, specifically if you're working with numerics, there's a really quick and easy way to do create vectors that are slightly longer, as long as they're contiguous sequences. Okay, and so I'm going to show you this in action. So if I do 6:10, now I get 6 through 10. Okay, and now we had the question earlier about this number 1. Right, and so this is really corresponding to like how many entries on this row, and it matches your console window. So it will change depending on your console window. It changes when it folds. So if I give you an example now, where I go to, I want to put 1 through 100, you can now see, like in reality, it's very easy to know like what entry you have before it kind of folds over. But here it gives you that information for free. So we know on the 23rd entry, it's now folded onto a new line. And on the 45th. Okay. But also if I do this and then rerun it, it should look different, right? Because it's adjusted to my console window. So it's just like a little trick that you pick up as you go. When you start to look at your own data a little bit, it just is a little shortcut for when you want to count to a specific entry. Okay, so this is vectors, and that's how you can produce numeric vectors very quickly. Oftentimes, what we want to do with vectors is we want to find specific entries. Okay, and so this is a process called indexing. And so whenever you come to indexing, you start to look at square brackets. And so if I want to ask the question, what is entry number 1? I will take my vector, which I've stored here. So I've got a vector. This one is a character vector, so it's made up of characters. And that is kind of given away by the fact that you use quotation marks whenever you want to use put a character into R. And so we use the combine function in exactly the same way to create our character vector, and we create this variable called z. And then if we want to ask what's in the first entry of z, we can use the square brackets z and then put a 1 in there. And that's just asking what's in the first entry. We can also ask what's in the 4th entry, and in this case it's returning d. Okay. So this is going to be an important concept. Indexing is maybe one of the most important operations we do, because you imagine later on you can start to ask these more complicated and nuanced queries where you're like, which row of my data frame is on chromosome 1 or something like that, and then you can start to extract data from data frames using this kind of indexing operation. But for now, all we're doing is grabbing the first entry or the second entry or whichever. Okay, and so you can also use vectors, numeric vectors, to index out of multiple entries out from another vector. Okay, so in this case we're using the combine function again, and we're combining together 1 and 4, and then we're indexing with this. So we're then asking the question, what's in the first and the fourth entry in our vector? Okay. And if we remember, we're doing it A through F, and so that's going to be A and D. It returns. And then the last part is what happens if we just want to exclude something? And that's where we use the minus sign. So if I want to exclude the fifth entry, I use the minus sign, and that's going to return everything apart from the fifth entry. So you can notice how it's exactly the same, except E is now missing. Cool. So that is kind of the basics of indexing, okay, and how to extract stuff from your data set. Okay. What we can also do is keep working with this assign operator to assign back, to modify. And so in this case, we have our Z. It contains A through F. And if I want to say I want to replace the fifth entry, I can replace it with hello. Okay, this is just another character. It's just a bit longer. And now you can see in the fifth entry, the E has been replaced with hello. Okay, so you can start to modify your vector, modify what you have going on, and yeah, manipulate your data set. And so again, this is similar to what we did actually here. Here we're using, and this we create this numeric vector, and then we index using it. But you can also just use the variable. Okay, so we have this variable y. It corresponds to the 6th through 10th entry. And now we're indexing and saying, we want the 6th to the 10th entry to be hello again. Okay, and you actually notice here that initially it was 6 long. And so it replaced the 6th entry, but then it was like, we're going to add the additional ones that you requested as well. So it's very mutable, very easy to change what is contained within your vectors. It's very easy to just keep using this assign operator, and you keep updating and keep changing. And so this is a key thing that we're going to see forward. We're going to do some more complex indexing later, but it's important to remember that square is for indexing, the parentheses is for anything to do with functions. Okay. Cool. So the next part is the math that we were doing earlier on can be used on vectors as a whole. And so when you're working with numeric vectors, you can then do math on the whole thing at once. Okay, so this is again important if you're ever doing any kind of like normalization or something like that. You can do a scaling factor to everything. And so in this case, right, we have our x, it's 1 through 10, and we're just going to times it by 2. So we use the little star to do multiply by 2, and now we assign it to y. Okay, so I'll show you this in situ. So we create x, we create y. And so y is a product of x. It's x times 2, and you can see that. And you can do things like a plus y to add them together. You can do any kind of math. And you'll notice when you do this plus y, that is doing it in, if your two vectors are the same length, it's going to do it in a position-specific way. So it's going to add position 1 to position 1, position 2 to position 2. It's not going to be adding just sums of everything. But this is important to know. It does this if it's the same length. If you have different lengths, then it will try and do something for you, but it might have to like fill in the additional missing part where it's mismatched with it's kind of refills in from the beginning again. So you can see here, if I'm doing x plus 1, 2, so this is only 2 long at this point. It's going to add 1 to the first one, 2 to the second one, 1 to the third one, 2 to the fourth one, etc. And then if they aren't multiples, it will give you a warning. But this part is a little bit dangerous because it doesn't give you a warning. Okay, so if you've accidentally have 2 different size vectors, but they happen to be a multiple of each other, and it's a mistake, you won't know that you may have a mismatch. Okay, so it's just something to be aware of. You can always use the length function. You can always keep an idea of what your vector looks like, and keep an eye on everything to make sure it's exactly what it should be. Okay, so next we're going to talk about a very special class of vector. Yeah, we can look at this again. Yeah. So what we have here, right, is I can put this into R. I'll just do this. So if we look at x, we do length of x is 10 long, and I want to add this. So it's a combination of 1 and 2. If I look at the length of this, it's 2, right? It's got 2 entries. And so that means when it adds them together, instead of doing position 1 and position 1, position 2, position 2, there is no position 3 match, right? So it recycles and it keeps using it. And so if I do the actual addition here, right, it's adding 1 to the first position, it's adding 2 to the second position, it's adding 1 again to the third position. And so it keeps repeating. Now, if I do this with a slightly longer vector, 3 doesn't go into 10. There's a leftover. And so it gives me a warning. It still does it. It's going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, and then 1. But this isn't typically what someone does in R. So it's giving you a notice to say, hey, this looks funky. It's going to let you do it. It's not going to create an error. Sometimes you'll do something and it'll create an error and it will stop you from doing it. But this is just giving you a heads up. Okay? Yeah. To undo it. So that's when you're doing assignments, you are essentially overwriting it. So no, but what you should be doing in any of your operations is, at the very least, you keep track of everything you do, right? So as you perform operations, you keep a track, and then once you've got, like, I don't know, you have like 8 different things in here. Let's say we'll just do those 2. You can run the whole thing. Okay, so you can just run this, and then you restart again. Okay, you can also save different intermediates as well. So once you get to more complicated analyses, it's really important to continually save out, so you don't have to reproduce this like metadata or intermediate files, things like that. But it's a good question because it gets into like good coding practice and how to do that. But yeah, the number of times I've accidentally overwritten something and then had to spend several hours reproducing exactly what I did it's too many. Okay. So next we have a special case, which is a vector, a special kind of vector. And so this is not for numbers, or it can be for numbers or it's mostly for characters, but it's all about categorical data. Okay, and so what we mean by this is, do you have a specific set of options that you think your data is going to fit into, and something you know ahead of time? And so, like, a classic example is if you're collecting metadata for some kind of study, or you have some mice, you're getting your metadata and you have their sex, so male or female, right? And so those are 2 options that you're providing as a factor. Okay, and so initially we create this vector, okay, just as we did before using the C, and then we use the factor function on it. And so now if we compare, if we look at what that looks like, we actually get this new output here. Okay. And so in this, what is being reported back by your ask session is this entry called levels. And so what this is some additional information in your vector that's saying, hey, this vector can either be female or male. Okay. And so you can extract this specifically out with the levels function. Now, why would you do this? Like, what's the use of this? By categorizing your data, it can help you prevent there being like errors, like if there's mismatches, say, like when someone is typing in the data or doing some kind of data entry, if it doesn't match up correctly, you'll be able to pick that up. It also allows for rapid summarization. And so you'll see this later with plotting, but also there's a function here called summary. If we apply this summary function to our vector, it gives you just some background on what this vector looks like, right? It has a length of 4, it's a class of character, useful information, but it doesn't tell you anything about the data. But if you've already told it that it's a factor, it knows that it can summarize it based on the contents of your factor. And so it will give you some totals based on how many females and males you have within your group. And so typically when you set this up, if you just do the factor argument like this, right? What it's going to do is it's going to look at the vector, and then it's going to create levels based on what exists within your vector. And then it's going to put those in alphabetical order. So you can see here, female comes before male. But maybe for your study, maybe your control group is the male or something like that. And you want that to show first before you see female. Okay. So then you can directly control the ordering and what levels you have by directly specifying it in the levels argument. Okay. Doesn't affect really much here, but you can see now that the levels, it appears male, then female, and the reporting out. This gets really important when you get to your graphs, because if you're going to create a bar plot from this, you can then control the order with which your categories appear. Okay. There is a specific class of factor called a nominal factor. And so when we consider male and female, there's no kind of order between them necessarily, like related to their properties, okay? But for some things, even though it might be a category, there might be some like preferential order. So when we use this function here, we're using a logical operator. We're asking, is factor example 1, so is male less than female, okay? R gets confused because you're just like you're providing it with 2 characters and it's asking you to differentiate them with like a greater than sign or a less than sign, and it doesn't know what to do. And so that's why it gives you this warning. It's not meaningful for these factors, okay? But we can use this with specific categorical data. And so, for example, here we just have some very simple things where we have small versus big versus small, right? And so by providing the argument ordered equals true, we now know that small comes first, is smaller, and then big comes second, okay? And then when you do this, look at the levels, it has the ordinal information between it. And it can then evaluate, is your factor example is small, less than big, okay? And so this allows you to add more complicated nuance to your example. Okay. So as you can imagine, if you're creating a factor and you're saying a bunch of levels, and these are specific categories that you expect your data to fall in, then if you try and add something that's different, R gets upset. Okay, so let's have a quick look at that. Okay, so we have our factor here. We have big, big, and small, and we have these two levels, big and small. And so I can overwrite. I initially created it where there was a small, two bigs, and then a small. And I provided I assigned a new value for the first entry. Okay, so we overwrit it. It makes sense. It went through fine because big is one of the two options, right? But if I try and do this again, but I change it to bigger, it gets upset because it's not one of the two options. Okay, and so this is a nice way of kind of gatewaying your data. It prevents like the wrong thing being inside your categories. So to deal with this, you need to do an update of your levels. And it's very simple. You can just use the levels function and the assignment, and you just assign a new option. Okay, so in this case, we're using huge, not bigger, but we do big, small, and huge. We assign that into our levels. And now huge is a possible option for assigning. Okay, so we're just expanding the purview and the potential options. Okay. So that's factors, and that's pretty much vectors for now. Okay, and we're going to move on to two-dimensional features. Okay, and so the one we're going to focus on is data frame. And so this is one of the bits that's maybe missing from the abridged section versus the full course. We have a section about matrices. Matrices are very similar to data frames, except they can only handle one data type. Okay, and so typically, most of the time, I'm working with a data frame, not a matrix. But a lot of the same rules apply for whenever you're handling something that's two-dimensional. Okay, but yeah, pretty much all programming language have this kind of concept of a table, and in R, it's the data frame. And so, because it's the way it's set up, and I kind of gave you that clue there, what's different with a matrix, it can accept all the different kind of data types that you want to give to it. So we've looked at characters, we've looked at vectors, we've looked at numerics, and it can have all of those stored in it at once. And so we can see here we're setting up a data frame. And so what we have here is 3 different vectors. Okay. You can see that one's called patient name, one's called patient type, one's called survival time. Okay, again, numbers, factor, and characters. And then by using the function data.frame, we can create a data frame. Okay, and so what we're doing here when we do the data frame, each argument that goes into it is going to be one of your columns. And specifically, we are defining the names of these columns as we're creating the data frame. So this first column is going to be called name. And so we say name equals this first vector that we made, the patient names. Okay. Then the next one is going to be type. So that's going to be type here. And it's going to be from the patient type vector. Okay. And so you can see how it's quick. You can quickly and easily build these two-dimensional arrays from these one-dimensional vectors. And so then when it comes to indexing, you imagine it's going to be a little bit more complicated, right? You're not just thinking about things in 1D anymore, you're thinking about them in 2 dimensions. And so to deal with that, you still use your square brackets for indexing, but now you're going to have to give it two values. You're going to have to give it like an X and a Y, essentially, or a row and a column. And so the first entry you're going to give it is going to be your row, second one is column. And so if I have my example that we just generated, if I'm going to index it, I can put, I want to look at the second row and the first column. Okay, and so that's going to extract second row, first column, and we get back patient 2. Okay, and so that's what happens if you want to get an individual point from a data frame. Now, if you want to get more than one point, you will extract out a vector, right? If you're going to ask for the entirety of a row or an entirety of a column, you're going to have one series of numbers or characters or factors, and they'll come out as a vector. And so in this case, we say we want to get the second column. What we do is we ask for the second column, and then we give it no information about rows. So you just leave the row section blank, and it will drag out the entire second column. And so you can see that here. Oh, I need to plug my computer. Yeah, and so you can imagine, you can see it the same for rows as well. So in this case, we're extracting the third row. Cool, we're good. Nice. So yeah, we're extracting the third row here, leaving the column blank, and we get back the third entry in our data frame. Again, we can extract out multiple things at once. And so in this case, we're going to say we want the second and third row. Now, as you imagine, now you're extracting out multiple values in the kind of row-wise and multiple values in the column-wise. And so that returns to you just a smaller data frame. And so in this case, you can see we're using the C, the combine, 2 and 3, and you get back this data frame. Replacement assignment works in exactly the same way. So we just keep using the assignment operator. We can assign into individual cells within your data frame. So you can see I replaced the first entry and the third column to forever. But again, this rule with factors still applies. Okay, so if you want to put something into a factor and it's not one of its levels, the factor information is still contained within the data frame. One way to think about data frames is it's basically a collection of vectors, and it's retained all the information about it being a vector, but it's just stuck them together. And so that means to be able to do this, you're going to have to do an update first. So again, let's have a quick look at this. So we have our DF example. And so we can extract out the second column, right? And look at the levels of it. One part that we haven't touched on here, another alternative way of indexing is we can index using the name. So I can index in exactly the same way with the name. Okay, and so at this point, I'm just asking what levels are present here. And it's very easy to then, I can take the levels from my existing vector. I can then combine that with a new level, which in this case I'm doing other, and then reassign that back. So this is often how we do modifications. If we're just doing a simple addition of one new thing, we'll take the old thing, we'll combine it with something new, rather than write it out wholesale every time, okay? So there's just kind of like a logical way of doing things. Yeah.
Why did we get upset when we changed this route?
Pardon?
Why was it not an issue when we changed this route versus the next?
Oh, okay. Yeah. So why did it not get upset about changing survival time to forever? Okay. So survival time is not a factor. Okay. So factors are the only kind of vectors that have this kind of specific category associated with them, where they have to fit in specific boxes. Everything else, and in this case, this is at the moment, it's a numerical vector within survival time. That doesn't mind what you put in there. What does happen, it does have consequences though, because it's expecting a number, and I put a character in there. And so you can't, in a single object, so like a vector, you can't have mixtures of characters and numbers. And so what it does is it changes everything in that column to a character at that point. So it'll be hard at that point to do any kind of math with any of the rest of this. So it does change it, but it doesn't object. Okay. So in this case, we've just updated the levels, right? And so then I can add modifications to, say, the sex here. And now we have male, female, and other, and it's not getting, ours not getting upset about it because it's been provided as an option in the levels. Okay. So there's another trick for indexing beyond using names. You can also use the $sign, okay? And this is actually one of the most useful tricks because it also auto-completes, okay? And so, especially when you're working with larger data frames with lots of names, it can be hard to remember exactly what they're all called. And so, when you just use the $sign and then you provide the name, it will give you the output just like you index specifically for that column. And I'll just show you the auto-completing. So say I have beginning of the name. If I then press tab, it will then auto-complete. If there's multiple options, it will show me the options and allow me to scroll through them. So the tab is super useful as you get more comfortable with coding because it gives you the ability to auto-complete anything that's already in your environment. It also applies to, say, I just have df, right? It now gives me an option for several different functions and this variable that I made myself. So I can then auto-complete that. Okay, so the tab is super useful and the $sign is really great for utilizing that. The other part about the $sign is it allows you to create things on the fly. So if I want to create a new column, I can just do $sign, give this new name of this column and provide the data to it and assign it in. And as long as that name doesn't exist already, I'm not going to overwrite anything and it will just be added to the end of my data frame. So in this case, I'm just creating a new column with new data in it. Okay, that's all I'm putting into it. I'm just asking for it to repeat new data 4 times, and it does that, and it's going to add that into the new column.
Can you do that as well for indexing?
Pardon?
Can you do that as well for indexing, like square brackets?
Can you do that with square brackets? So if you put the name into the square brackets, and I don't think so, but we can give it a go. Let's grab this option. So that's it working normally. So now we have, and then that's new column 2. Oh, maybe it does. Yeah, it does work. Cool. So you can update it whichever way you want. Yeah. Okay, that's a good question. In the next, after the break, we're almost at the end of this section, we'll start to talk about ordering and reordering things. For this very simple example, I would just manually do the order. But once it gets to much more complicated things, we do things called merging. So you might have one data frame and another data frame, but they have a shared index. And then you can merge it and make sure everything matches up. Or you can order things based on that number and things like that. Yeah. And so something key I want to drive home when you're working on these R operations is it's really important to know what your variables look like, what kind of properties they have. Whenever you do something to something, it's really important to know how big it is, like what, so you know what you kind of expect from like any kind of math you're doing or the subsetting you're doing. And so it's really easy to do that using these group of functions, dim, nrow, and ncol. And so you're getting the dimensions, the number of rows, and the number of columns. And so these are the data frame or 2D version of length, right? So we use length when we were doing vectors. Dim, nrow, ncol take care of a lot of this for your anything that's two-dimensional. Okay. Yeah. And then something we touched on is names. And so we've seen how you can add names just kind of custom into your data frame. Or when you're setting up your data frame to begin with, you can assign the names then. But if you want to update a column name or a row name, you can use the col names or row names function. What that does, it extracts out, if you just use that function as is, it extracts out all the names as a vector. So I can ask for the column names here, and it gives me that as a vector. But if I want to do an update, I can just keep using this assign operator. This assign operator just keeps working. And so say I want to update the first entry of the col names. At the moment, it's just name. Maybe a more appropriate name is patient ID. And so what I can do is I can assign that into the first entry. Okay, so a lot of these things that you're learning, you can just keep reusing over and over again. Other ways to kind of augment your data frame is by using the bind operations. So cbind, what we did here, if you're with this, is we added a vector to a specific column. But you can also do it by using cbind. And so what that's doing is it's saying, I want to attach X to Y and have them next to each other. Okay, and this can be really useful, especially if you say have multiple data frames and you just want to stick them together. You can use cbind for that as well. And so you can see here, I'm just adding X, which is the value of 1 through 4. I'm adding some like indexes or something like that. And I'm adding it first, and then I have my original data frame. And I'm creating a new data frame from this. Okay. rbind works in much the same way. So we have column binds, that's what we just did. rbind works in the same way, but it's binding by rows. So quite often you might be in a position where you've done one trial of an experiment and you're doing a second trial, but you want to put them all in one data frame. And they have all the same columns, so you just use rbind and then stick them all together. And then you can do whatever plotting you want after that. Okay. So we're nearly done for the first session. I think I've gone a little bit longer than expected, but I think I normally do that. So the last thing we're going to cover is lists. And we'll very briefly go over these. They're pretty straightforward, but incredibly powerful. Lists are a hodl for everything. They're basically a little container that you can put anything inside of. Okay, and so say in your analysis, you've created a vector that has a bunch of metadata information, but you've also created a data frame which has a bunch of numbers, which is your result. And maybe you also have another metadata like data frame from somewhere else, but you want to keep them all together in one object. And so you can do that with a list. Okay, so a list just has multiple kind of holders within it. It can be as many as you want, and you can just put whatever you want inside of it. So in this case, we're creating these 3 different elements, right? And here, this one is, say, this is just the number 10. We have A through D, and then we have this data frame. Okay, so in this data frame, we have some numbers and some characters. I can then use the list function and it's going to group them together. Okay, and this creates a list. And if we look at the output, if we just like ask to look at what the list looks like, you can see we have the first entry here, and that contains 10. We have the second entry within the list that contains your A through D, and your third entry contains your data frame. Okay, and so something you maybe notice here is we start to see double square brackets. Okay, and so this is an important thing when you see lists. You'll quite often see double square brackets. There's a nice little clue that you're working with a list. And the double square brackets also play a really important role in indexing with the list, right? So if I want to just take out the first entry from a list, say, in this case, I have the number 10 in slot 1. And if I give it just a single square bracket like we've been doing with everything else, what that does is it says, I want to grab the first thing, but I want to keep it as a list. So what you get back is a list that's only one long, and it contains the number 10. And so that it still has a lot of the properties of being a list. So you can't interact with it in the same way as you would just like as a vector, so like a number 10. And so you use the double square brackets to specifically drag it out of the list format. And it returns what you put inside of it. Some things work in the same way though, so you can actually use the combine function with a list. And so that expands your list by doing that. So in this case, we create the list again, and we've used the C function, and we're adding in a fourth entry here. Okay. And so by using the C function, we can then make our list longer and longer. Okay. And so this is like, we're not really getting into the power of the list here, but just conceptually, it's this kind of placeholder where you can just put lots of stuff. It doesn't matter how long they are, it doesn't matter what format they are, but you can put them together. And so anytime, I think that the biggest one, that especially when you're starting, maybe you have like multiple results, but they're all of different lengths. You can't put that in a data frame because they're different lengths and it won't make us a rectangle anymore. So a list is your alternative at that point. And then once you create a list, it's very easy to uncreate the list using a function called unlist. And what that does, it goes from this complicated structure with all these entry points, and it just flattens it down into nothing. Okay, and so you end up with this one-dimensional vector containing everything that went into your list. Okay, sometimes this is really useful and important to do. Other times you lose all structure and it becomes really hard to then decipher what to do. So there might be better ways to kind of combine your data sets into something that isn't a list. But an unlist is a good place to start. Okay, so the time is 2:20. I have here, there's some exercises, but I also understand we've been going for like over an hour at this point, an hour and 15 minutes, I think. So if people need to go for a break, get a coffee or whatever, they can. And we will probably, I think, let's see, I'll start, if anybody's gone over the exercises and had a look at them, I can review them as a group at 2:45. So it gives everyone like 20 minutes to either have a break or to play around with the exercises, whichever. And then once we review the exercises, that should take about 10 minutes. We can then start on to the second half. And so in the second half, we get into the really kind of nitty-gritty of manipulating your data, asking questions like, I want to order them based on number. I want to extract out a specific field based on whether it's in a certain group. And we'll also start looking at loops, if statements, and things like that. And then a little bit of plotting at the end. So that's the real like meat and potatoes of what we end up doing. Okay, cool. If anyone has any questions or has any issues with installing as well, I'm around to help. Okay, I'm going to pause the recording for now. Okay. Okay. Right. To the person that's having trouble with the RStudio, hopefully Doug can help, but it seems like you might need to reinstall. Right, but we're going to go through this. So what I'm going to do is switch over to this. And so those are the exercises. We also have all the answers here. Okay. So the exercises are kind of designed to give you a run through of all the things we kind of covered at the beginning or the first session. None of it should be too complicated, but there are some which maybe take a little like a mental leap, ask you to combine a couple of things that were in disparate parts of what we covered. So if you struggled at any point, it's okay, it's normal. And so to start with, all we're doing is asking you to create a vector, right? Containing the values 1 to 5. And so the big thing that I think people sometimes get stuck on when they're doing this for the first time is they won't do this, right? So like this is the answer, but they'll do this. And they'll forget to combine, okay? So when you do that, it gets confused because you're trying to assign something which isn't a fully fledged, fully shaped object. You have the 1 through the 5, but it hasn't been told that they should be stuck together. Okay. And often when it gets to this, it's saying that you have an unexpected comma. Really, this structure is associated with functions. Okay. And so you really need the C in there to do that. Actually, this is a function we haven't covered, so this might be quite tough. But actually, I'll do it one at a time. Create a vector containing the values 1 to 100. Okay, so as before, we just use the colon, right? Colon allows you to rapidly create a very large numeric vector of varying size. Okay, so create a vector containing the values 0, 5, 10, 15, and 20. So there's a couple of ways of doing this, and this, I think, gets something you'll find in coding in general, something that's definitely true in R, is there's normally 3 or 4 ways of doing every single thing that you want to achieve, apart from the very most basic operations. And so we could obviously write in C 0, 5, 10, 15, 20, okay? And I'm sure that whoever's answered these questions probably did exactly that, okay? But there is a function that takes care of these patterns for you. Anything that's repeating over a constant interval, you can use the seek function, okay? And so if we break this down without the help, okay? Without looking at help, we can probably figure out how this is working anyway. We want to go from 0 to 20, right? And so those are the 2 first arguments. We're going from 0 to 20. And then we want to do it in steps of 5. And so that's the third argument. Okay, 5. And so by using the seek function, you can then start to build some of these more complicated numeric vectors. And building these vectors, like why are we doing like building all these weird numeric vectors with like 1 through 100 or this repeating pattern? Sometimes you'll want to use a repetitive pattern or extract out specific information from a data frame over a specific region, right? Maybe you want every 4th entry. Maybe you want only to look at the first 20. So by constructing these specific numeric vectors. It's how we often do indexing later on. Okay. So next, create a new vector with all but the first and last value of the previous vector. Okay. So I'm going to break this one down because it gets a little complicated. But we want we want the first value, all but the first value and the last value, okay? So when we're indexing, we want to be able to get to find the first value and to remove it, and we also want to find the last value and remove it. So if we knew that this vector is 100 long, for example, in this case, it isn't the same as the vector I used in the example, but it works the same. If I know that this is 100 long, I could specify, right? I could do 100, and that will work exactly the same. But this gets to a thing that we call hard coding in any kind of coding, is when you add a specific value to something which could be a variable or something that's a bit more abstract. And so by doing this using the length function, what we're doing at that point is saying, well, maybe next time I run this code, the input vector is going to be different. And that means my code will be able to handle that difference. And that's why this code still works when I look at 1 to 100 and still removes the last one and the first one, and works in exactly the same way as if it is 0 through 25. Okay. So this is it's one of those things, as you get more proficient, you'll start to look at ways to abstract your code a little bit more to make it more efficient. And most importantly for you, to make it easier to repeat. So you don't have to rewrite something hundreds of times. You want to, this whole point of what we do is to make your life easier. So you don't have to hand calculate stats and things like that. Okay, so that was some interaction with vectors. The second part of the exercise is about data frames. Okay, so first it wants you to create this specific data frame. Okay, and again, this is basically testing to make sure that people use the C combine function. Okay, we provide all of the values for you. Okay, and so we provide all of them here. They already have parentheses, they already have quotations if they're characters. And all you need to do is copy and paste them, add the C, and then input them in the data frame argument. Okay. The other part is you need to add the names as well. So we need to remember, how do we get names? Either when we set up the data frame, we provide the names as in the data frame as one of the arguments, or we come along later, we create the data frame, and then we use the call names function to add the names in after that. Okay. Yeah, all we're doing here is creating this annotation data frame. Everyone's struggling with it.
Yeah, it's very.
But yeah, so next we want to add a column to this data frame that we just made. Okay, and so we showed you an example earlier using the $, right, where provide a new name to the $, and then you assign into that. But as we also showed, you could also use this square index brackets as well. Okay. There would also be a third way, right, where you do cbind. Okay, so again, it's multiple ways to get to the same goal. Then you want to subset the data frame to only the first 2 genes and remove the ensemble IDs. Okay, so again, this is just indexing. We want to get the first 2 genes. And so we index on the first row and the second row, and we're removing the ensemble IDs. And so that's the second row. Okay. So we're using a combination of exclusion and inclusion at the same time for the indexing. We do something similar again. Subset the data frame to the last 2 genes and remove the 4th and 5th column. Okay, very similar to what we did, But again, I give you a nudge here. Try to do this without giving it the size information for the data frame. So this is similar to the code that we used earlier for the vectors, asking you instead of giving it the specific length of the data frame or the number of rows, I'm asking you to calculate that and use that within the operation. So what we're using here is the colon. We ask how many rows does the annotation have? We subtract 1 away, and then we do the colon to the number of rows. And so that's going to give you a range. We can look at this here. I'll have to. So if we did n row annotation, we do n row annotation -1, we do that. To n row. Right, we have 4 and 5. Okay, so if you follow that, I've asked for -1 of the total number of rows to the total number of rows, and that'll give me the last 2 entries. Okay. And then I just use that for indexing. And then the last part is just asking you to do some assignment again, but doing some math first. Okay, so something to remember, keep remembering is any of the numerics can be still used for all the arithmetic. So we can take our expression column, we can divide them by the gene lengths that we just added, and we can then create a new column, which is going to be our length normalized expression, and we can add that back in. Okay. And so this kind of iterative math and addition to expansion of your data frame is a very common step in what we do, right? We're going to be continually doing math, doing some normalization, doing some kind of counting, doing some kind of differential, and you just keep getting a bigger and bigger data frame. Okay. Cool. So that is the exercises. I hope they all make sense. What we're now going to switch to is session 2. So there's quite a lot of topics within this one. It hopefully should take about the same or a little bit less time, but there are maybe more complicated topics, okay, and maybe the most useful topics at the same time. Okay, most of the time we aren't going to be creating data inside our console. We're going to be reading it in. Maybe you've done some qPCR. Maybe you've got some count tables from GEO. Maybe you have some metadata, things like that. And so you can be, we talk about reading and writing. Then it's going to get into the data manipulation. How do you actually start to interact with your data to extract the useful parts or to summarize it in some ways? We'll talk about doing some kind of conditions and loops, and then we'll have a little bit of plotting. Okay, so yeah, this is just what I said. Most of the time, you won't be generating stuff in R. You'll be reading it in, you'll be changing it, and then you'll be exporting it. So hopefully everyone's downloaded the course material at this point. If you haven't, you can go to the home page again. You can click on this link here. And what it's going to do is it will download let's have a look at my desktop. So I've downloaded it here. It's a zip file. You can unzip it, and then inside it is all the information contained within the course. And included in some of that is some spreadsheets, okay, and some text files. And we're going to try importing some of those. Okay, but to be able to import them, first we need to find them. Okay, and so something we met earlier was the dir function. Right, the dir function is a function that tells you what's in your directory. But sometimes we want to know what's in our working directory and where our working directory is. So we can do git wd. Okay, and so everyone will have a different result from git wd. But really the way to think about a working directory, it's R's view of your computer. Okay, it's similar to if I open up Finder or Windows or whatever, and I've gone to my documents, I'm sitting there, that is my viewpoint on your file system. At that point, I'm in my documents, so I'm on desktop. Here, this is where R is looking from. And quite often you might want to change this. Controlling this gets really important when you start to manage your projects and things like that. But for what we're doing now, what I want to do is reorient everyone's working directories so that they are inside the download that they just got. Okay, and so we're going to move to inside the download for the course materials. And so for me, to do this, I need to do set wd. Okay, and then I'm going to use the little tilde, and that gets us to my home directory. And I know mine's on desktop, but I know a lot of yours might be in download, for example. So I could go to downloads and look within downloads for it. But I'll go to, for me, I'm going to go to desktop. Okay. And so then if I look at desktop, I have some options here, right? And I know maybe it'll have a slightly different name, but I know once I've downloaded this course material, it's RU intro to R abridged. It might have master appended to it, it might not, it might have some numbers. It depends on your system. Okay, so now I'm telling it to move into there. Okay, but I haven't finished yet. I specifically want to move into the R course subdirectory of this. Okay, if you can do that, and what I'll now do is if I do git wd, now instead of being in the desktop, R thinks it's in here. And if I do directory function, I see a different set of things. What I can see is the presentations. I can see the exercises. Most importantly, for what we'll do, I can see expression results and data. Okay, these are two places where we've got some data stored in the course material that we'll read in. Okay, there's also ways to do it in RStudio. I think it's in session, you can set your working directory as well here. But it's good practice to figure out how to do it. Command line, like RStudio has so many ways to make your life easier, but sometimes it's better to just know how to do it the R way. Because it's good practice. Okay. So once you've set your directory at that point, this code will work. Okay. Is anyone having trouble finding their working directory or getting it to the right place? Yeah? Yeah. Pardon? Okay, yeah, so I'm hitting tab to do that. So tab is the autocomplete option. So I can show you again. So when I'm doing set WD, like at this point, when it's half complete, I press tab and it comes up with an option. And then I can press enter and it will complete it for me. Cool. And so, yeah, for most of you, I'm assuming it's going to be under downloads. But it's wherever you downloaded it to, and you'll have to unpack it first. So it comes as a zip, so you'll have to double click on it to unzip it first. Okay. But yeah, once you're there, this code will work. You can also, if you wanted to, I could write in. What I'm doing here is I'm reading a table in. Okay, it's using the function read.table, and I'm telling it where the table is. This table is a CSV table. Okay, that means a comma separated table. There's lots of different kinds of these things, and I'll also show you about Excel specific formats as well. But what I'm doing in the first argument is telling it where it is. So if you wanted to, You could also go desktop or downloads, and then intro to R, then R course, then data. Then you can do it the long way. But by making everyone navigate to the same area, then this code should be the same for everyone. So it's whichever like preference you have to a certain extent. And what you'll notice that beyond telling you where it is, it's also I need to provide it some information. I'm providing two other arguments. Sep is comma and header equals true. Now, sep is comma. This is a comma separated file. So the comma is sitting in between the values. And so what do I mean by a CSV? Okay. This is what the file looks like. Let's zoom. Yeah. So this is what the file looks like. And you can see at the top, we have column names. And then in between each data point, there is a comma. Another common data format that you might run into is a TSV. It's often, a TSV is often, if you see a .text file, they're quite often TSVs as well if there's some kind of data frame. And what a TSV is a tab separated file instead, okay? And so by recognizing a CSV or a TSV, you'll know how to read this in. And so with this, we can then use that to guide how we do the reading in. And so we want this separated to be a comma, and we want header equals true. So that means there are column names. So I want them to be read in as column names. If I put header equals false, the first row in my data frame would be the column names, which wouldn't be a valid data input like entry. Okay, but this time it knows that actually I want the first values to be column names. Okay, and then I'm subsetting here for the output just because it's quite a big data frame for my slide. Okay, but what you can see here is it's read in the data frame. You can index in exactly the same way. And we've managed to get data from outside of R into R with relative ease. So read table is really great. There's tons of arguments associated with it. There's things that allow you to skip rows. There's things that allow you to do all kinds of things. So you can dip into that function, have a look, see if you've got a weird file. I'm sure it's got a way to handle the input. But one of the other big parts is at the moment is what we did. We read this in with the column names, but it actually had row names as well, or you could consider these to be row names if you wanted to. And so by saying row name, using the row.names argument and setting it to the first column, so it equals 1, you can then read them in as a row name. Okay, so it's giving you some options here about how to read them. Read.table also works with URLs. Okay, so anyone who's had issues so far getting access to the table, reading it in, you could just use this URL and it will read it off of our website and it will come into your R sessions from the internet. Okay, this is also a really nice way of like if you're working with, say, something like GEO or something like that, you might be able to, if you get the path, you can read it directly off GEO rather than downloading it to your computer and then putting it into R. And then if we've got read.table, the converse is going to be write.table. Okay. And so a lot of the same arguments are going to be present. So say you read in a CSV file, you could always choose you wanted to have a different separator for out. Okay, so you provide the separator. In this case, we're just going to write it back out as a comma again. But you could instead use a tab, or you can use whatever you want. But obviously, sticking to conventions is better if you're going to share it with someone else. Okay. And then, yeah, in our case, we have no row names. Because really, this should be considered to be a column. So we have no row names, we have column names, and we want to separate it. So we say row names equals false, col names equals true. Okay. And so this means that when it writes it out, it's actually going to write out the column names, but it's not going to try and write out row names. Because what we have here as the row names is just a bunch of numbers which don't mean anything. So you don't want that written out because it's just going to be a waste of space. Some other useful functions for reviewing your data, and this gets really important when you start to read stuff in that's bigger, is head and tail. So when I read something in, I didn't read it in yet. Give me a sec. This is always the first thing I do when I read something in. I do head. Okay, and it gives me the first 6 entries. I can also control the number of entries. Ooh, could you imagine that? So say I want 5 or I want 15. I don't think there's 15. But even just 1, okay? And so head is a really easy way to start to get to know your data. I think especially getting started, a big thing people don't do enough of is actually look at what they're working with. And so it's really important to keep on track of that. And then tail is the match for that. So tail looks at the bottom. Okay, especially when you have something, maybe you produce something with 1,000 lines, 12,000 lines, really, really long. You often want to look at both ends because maybe if you've made this data frame computationally, something might have gone wrong along the way. And you get a bunch of weird stuff at the bottom. And you won't know that unless you look at the bottom. The top might be completely fine. So by looking at both, you can actually check your data integrity and make sure everything looks okay. Okay. And so then we've talked, like I showed you CSV files, and that's something I'm very comfortable with working with. I work with CSV and TSV files all the time. But most of you, when you get something from a collaborator, when you want to export something to give to your PI, you want to say you created a really nice list of candidate genes, and you've got a gene expression and some other bits, but it's they aren't necessarily going to know how to look at a CSV file. It's not very like user friendly to like look at it like this, right? It's hard to pass. So you might want to export it into an Excel spreadsheet format. And I'm talking predominantly it's Excel, but there's also lots of other kind of proprietary formats that are more difficult to export and import from. And so Rio, which is like our input-output package, is designed to help you with that. And so hopefully everyone was able to install it. And if they weren't, it's just as simple as doing install.packages. And then you give the package name, and it's surrounded by quotation marks, and then it should install. I think a lot of you at that time got questions about whether you want to update other packages, which are dependencies for this. I'd say, just as a heads up, a good rule is to always say no and see if it works. Generally, when you're working in data analysis, you don't want to keep updating your packages super frequently, because if you're working on one project, you want the data analysis you to do to be reproducible, right? And so that means if you keep changing the package versions because you keep updating everything, it's going to be hard to make sure you get exactly the same result when you start and when you finish. And that gets even more complicated if you start processing something, then do an update, and then keep processing something. So the best practice is to not update, okay? And then when you finish something, then you can do an update, okay? Or there's ways to install multiple versions of R or control your environments. So if you're interested in all of that, the next time I run a workshop in like a month's time, we're going to be talking about reproducibility and how you maintain these things, okay? But for now, this is how you just do the installation, okay? But installation isn't enough. You have to then load it into your particular R section, right? And so once it's installed, it's installed for every time you want to use R in the future, at least that version of R. But in that particular time you're using R, you're going to have to use library to get it in so it's active with what you're doing in that day. Okay, and so we've loaded Rio, and now we have a whole suite of new functions available to us. And so it can, like Rio can handle all the like more like CSV and TSV, these more simplistic file objects. It can handle those fine. And so you can use the import function, okay? And you don't have to tell it anything. It figures out, it looks at the end, it looks at the fact it's a .csv, and then it figures out how to import it correctly, okay? And so in this case, we're just doing import, and it's imported it correctly, okay? But this is just the same as read.table, right? It hasn't done anything special at this point. Now I could use import on a spreadsheet, and it will import the spreadsheet, okay? And so this is what makes Rio very useful, okay? And then specifically, if you do this, if I was just to do it like this, let's do library Rio. Okay, it imports it, right? And I successfully imported it from this Excel spreadsheet. But if this Excel spreadsheet has multiple sheets in it, you can also specify which sheet you want to read from. So let me just double check the name of this guy, metadata. So there's also multiple sheets. You can use the which argument. So I can say I want the second sheet, and it gives me the metadata that's in the second sheet. Or I can actually give the name, which is metadata. Okay. And so this allows you to like a really useful way of interacting with Rio, with Excel, and handling your import and export. Okay. And so, as you can probably guess, if import is the import function, export is the export function. Okay. And all you have to do is much in the same way as what we did before. You give it something. So in this case, we're just giving it the expression scores, and then you tell it where you want it to write, and it will create the Excel document for you. And then you'll be able to just open this up in Microsoft Excel, and everything will be great. Okay, so that's your input output. So now you know how to get something into R. You want to be able to get it into R, do something to it, and then export it. And you want to be able to identify your candidate genes or whatever you're doing. And so the main operations, I've kind of given them broad names. It's ordering, selecting, and merging. Okay. And so we'll run through these three main operations, how they work, and what are the key functions for each of these. So we're going to start off by using this data set. Okay, and so in this data set here, we have one column, which is a bunch of gene names. We have another column, which is, you can't see all of it, but if I did tail my df, you can see there's an option, whether it's selected or not selected. So these are basically genes of interest or not genes of interest. We have a pathway, what pathway they're involved in. And then we have some kind of expression score. Okay. And so quite often when we do analysis, right, we care about the maximum or the minimum, right? We care about what's at the top of the list. And so to do that, we can use the order function. So If we do order, we can provide it via df. In this case, we're going to be interested in expression. Okay. See that? And so what we have here now is a numeric vector that's come back from this function, right? And what this numeric vector corresponds to is the order of values within that vector, okay? And so it orders them in a way that is from smallest to biggest, okay? So if I then, because this is a numeric vector, I can then use this for indexing. So if I go back to my diff.
Yeah, so you return the raw numbers?
It's, so no, it doesn't. It doesn't retain the original numbers at all. So
What was the error row numbers? What was the number 28 in the array that we just get?
yeah. So it's, yeah, whatever's the 28th value in rank. It's basically, it's like ranking. Yeah. But with that information, right, we can then go back to our original object and index with them. So if I was to say, go to my df expression, right, I now have reordered them in order, right, starting at 19 and going all the way to 74, right? But really, we want to reorder everything in the data frame. So then instead of providing it to that vector, I'm going to provide it to the whole data frame, and I'm only want to reorder the rows, okay, not the columns. And so I'm going to put this into the first part of the indexing and leave the second part of the indexing blank. And so now you can see that everything's been reordered based on the expression. Okay, and so we know gene 28 is expressed the least. We can scroll to the bottom. Gene 13 is expressed the most. Okay. More often than not, also in biology, we care about the max. We want it to be ordered in a way that's, we have the big number at the top. And so we can change our order to decreasing. We add this additional argument. And so what this is doing, right, it's maybe, I find this argument a little non-intuitive. Most of the time, the names in R is very intuitive. I find it a little non-intuitive, but that's okay. But it's decreasing, so it's going to go from biggest to smallest. And I'm going to turn that to true. By default, it's false. And now if I look at the top, I have the big number at the top. Okay. And so quite often when I start manipulating something, I'm starting to make outputs. I want to get my big number at the top, so I can actually, these are the genes I want to start focusing on. Maybe I have some tracks open on IGV or something like that. I can start to look at these genes and seeing what they're doing on the tracks as well. Okay. So that's what we just did. And we did decreasing. Okay, so that's ordering operations. Order is your main function for that. It works predominantly on numerical vectors. You can do it on characters if you want, but it's not as logical in that sense. I think it does it by alphabetical order, but like most of the time, that isn't something you're really worried about. If you want to order things with like a character, really you should be using a factor at that point. Okay. So the next part is subsetting. Okay, and so we've had a very brief touched on something that's called like a logical operation. Okay, and so if we want to start to subset our data, we want to be able to ask a question. And so to be able to ask the question, we ask it in a mathematical way, which is with some kind of logical operation. And so earlier on, we were looking at ordinal factors, right? And we were looking at big and small, and they have inherent hierarchical information between them. And so we know when we created this ordinal factor that big was bigger than small, right? And to do that, we use greater than signs. Okay, and we can do this on our vectors to ask these questions as well. And what we get back for these questions is we get back a logical vector. So this is the last kind of vector that we'll be introduced to. But what a logical vector is basically a series of trues and falses. Okay, and each entry is the answer to that question that you pose to it for each point within your vector. And so this is really like important, because if you want to be able to say like which ones in my vector are glycolysis genes, or which ones are above a certain value, you can use these kind of questions. So here we're looking at the expression data within our data frame, and we're asking which ones are greater than 70. Okay, and specifically this is an ordered data frame. So previously I've ordered the data frame based on expression value. And so unsurprisingly, all the values at the top are true. Okay, so the first few entries are true. And so then the nice thing about a logical vector is, much like a numeric vector, you can use it for indexing. Okay. Okay, actually I skipped ahead. Well, there's lots of different other logical operators. Okay, so the one we've actually touched on a couple of times is the greater than or less than, but there's also the equals to. So this is looking for direct equivalence between two things. So you need to use two equal signs next to each other. Or you can say greater than or equal to by using the greater than or the less than sign next to an equals. Okay. And so using these as your logic, you can then ask these questions. You create these logical vectors, and then you can index based on them. And so in this case, I'm asking the question, is it greater than 70? And then I'm putting this into my rows as an index. Okay. And it only gives me back the true values. So this is the entire data frame now. Everything else has been filtered out because we don't care about it because it's below 70. Okay, so this is super powerful. This is like how you imagine, like you start to really manipulate your data, start to break it down into groups you care about and things like that. You can also combine logical vectors. So if you actually care about multiple categories, you can use either the and sign, the pipe, which is just the straight vertical line, or the exclamation mark, and they stand for and or not. Okay, and so using these allows you to combine these logical operations together. And so you can start to ask these really complicated logical expressions to really subset your data down to like the genes or whatever you care about the most. So in this case, I'm asking what is greater than 60 and is in the TGF-beta pathway. And so again, this is all the output from that. Everything else is filtered out. Yeah, what's up? Yeah. So that is a good question. So for those not here, the question was, is there a way to not have to do all this kind of assignment stuff and have to index back in? Can you just like filter it straight out and kind of skip the middleman in that sense? And there is. And so there is a whole universe, which some of you who are maybe a little bit familiar with R, there's a whole universe called Tidyverse, which is a whole community within the R community, which have a series of functions to try and make some operations more easier, streamlined, and things like that. And so they have a specific rationale with how they do things. They're incredibly powerful tools, and they have a function called filter. And so I don't introduce that into like this kind of workflow because it is a whole different logical step with how to interact with data. However, I do recommend everyone, once you get going, to look into tidyverse and to start playing with some of their functions, because it will make your code look nicer and it will make things go quicker as well. Okay, so there's definitely shortcuts, but based on the building blocks we've learned so far, this is maybe the easiest way to demonstrate them. And we do also have a course on tidyverse on the website as well, so you can go and look at that and start to play around with that. We spent a long time looking at filter. There's also some other functions like select and things like that are really powerful. Cool. So one example of the kind of ways that these logical operators we've used so far don't work is in if you have multiple things that you want to compare to. So say you have one long list of genes and you have a much smaller list of genes that you care about. You can't say, does this long list equal this short list, right? You could go through and ask every single question to every single row using like a for loop or something, which we'll talk about later, but it's very time consuming. So instead, there's an operator which just says, what overlaps with this other group, okay? And so this is the in operator. It uses percentages signs to kind of delineate the operator. So it's percentage sign in percentage sign, okay? And so when you're doing this, you're asking, what in A is in B, okay? And it doesn't tell you which one it matches to, but it gives you a nice true and false, like, is it present in the other group? And so when you run this, say we have, we're looking at the same data frame we've been looking at this entire time. It has a bunch of genes in it. And we have this gene vector that we care about. Okay, we only care about gene 1, gene 10, and gene 15. We can then say which of these is in our favorite genes. And when we do this, we should get 3 different trues, and we do. So the first one here, and one here. Okay. And so that's a nice way to then be able to select specific options from multiples. Okay, and again, you're generating a logical vector, so we can index it and we get back our 1, 10, and 15. So this is also an incredibly powerful tool. Okay. So the last part in like our data manipulation set is merging. And so quite often what we want to do is you may have one data frame you've got from one set of people, one data frame you've got from somewhere else. And the most common use I have for this is I might have a bunch of annotation data or a bunch of metadata, say with like patient information or something like that I've collected. It's been manually curated in some way. And then I have a bunch of results from an experiment, which are basically a bunch of numbers. And I may have the IDs associated with them, but I don't have any of the metadata. And so then when I want to start plotting stuff, I need to put them together, okay? And so that's where the merge comes in. And so a merge is going to use something that's in common between 2 data frames to then stick things together, and it kind of zippers them, making sure that everything is matching appropriately. And so in this case, we're going to read in a second data frame. Okay, so there's this data frame here. And let's have a quick look at it, my df2. Okay, and so this is a bunch of gene lengths. If I look at n row of df2, ooh, my df. Good. You can see I have 15 entries, okay? And then if I look at n row of my df, I have 100 entries. So you can tell I have 2 data frames, they have some commonality between them, but they don't match, okay? So that means this merge is going to be, going to result in some subsetting as well. So this is another way to subset your data. If you've filtered down, but for some reason you've done this manually, you've got it in a separate table, you can then use that table to filter down another table. And so the way the merge function works, it's just merge, you provide one data frame, then you provide the second data frame. You tell it what you want to merge by. So in this case, I'm saying by X, and this would be by Y, okay? And so what this is saying is my common column is called gene name in my DF. My common column in my DF2 is called gene, okay? And so it knows which columns are should be the same, where it should find matching partners. And then there's the argument all. And so what you can do when you merge is you can have like a very friendly merge where you keep everything, you keep all of the data. And if something doesn't match, it's just they put an NA in that column. But anytime it does match, something will be it will be carried across from the second data frame. Or you can set all equals false, and unless it finds a match, it's going to remove it from your final data frame. So that's what we did here, and we end up with just these 15 entries. Okay. And so depending on the way you want to merge, the way you want to keep your data and preserve it going forward, this can be either a really useful tool to either subset your data or to bring all your data into one data frame to then do some plotting or something. Okay, so that's merging. And those kind of series of steps are beyond my actually doing stuff at the bioinformatics tools. That is what I spend 80% of my time doing, right? It's subsetting data based on specific characteristics. And then the other 20% really is plotting it and making it look nice. So it's a really important set of tools, and it can be used from UStying with some very simple data sets you get from your qPCR all the way up to this really high level bioinformatics processes that I'm doing after doing this for many, many years. Okay. And so the next step we have in the presentation is about conditions and loops. And so conditions and loops are ways in which you start to automate some of the workflow when you're asking these questions or when you want to do something repeatedly. It's how you actually start to make use of the fact that you're on a computer and you have all this computational power. Okay, and so what we're going to start off by doing is we're going to be looking at an if-else. I think, yeah. And we're going to start by looking at if-else, and then we're going to look at for loops. Okay. And so an if-else is kind of this branching statement where you're asking if this parameter is met, I want to do something. For loop is going to say for this many times I want to repeat. There's another one which is a while loop, which I rarely use and is not covered here, but it is in the full-length course. So check that out if you want to do something that relates to, while this condition is true, I want to keep doing it. It just doesn't come up as frequently. And so I'm not going to tell you guys about it as a result. Okay, so if you think about an if statement, right, and this kind of if branching, what is fundamental to the bottom of it is you have this logical statement. You want to say, if something is true, I want to do something. And so you want to say, if this condition is met. And we have just spent a while talking about logic and logical operators and things like that. And so that's really the fundamental part of an if statement, is getting that logic set up so that something will happen when something is true. And so in this case, we have this question of just is x greater than or less than 4, right? Now, the if loop has a very specific structure. And so this is maybe the hardest bit about the if loop to learn. It uses parentheses. So it is like a function, but it also uses curly brackets, okay? And so whatever condition you want to be evaluated goes in the parentheses, and that comes directly after your if. And then you'll open your curly brackets, and then whatever you want to be evaluated, whatever thing you want your code to do when that statement is true, goes inside here. So in this case, we're just going to send a simple message. Okay. And so one big difference, maybe if people have other experiences with other coding languages, other coding languages care a lot about formatting. And so where there's an indentation, where there's a space and things like that, R doesn't care as long as you set up brackets right. Okay, so as long as you put them in the right place, I could leave a bunch of spaces anywhere. Okay, it doesn't give a damn. There's good coding practice, good formatting practice, but ultimately the code will still run. Okay. And so in this case, I have X, I've assigned it to the value of 10, Y, I've assigned it to the value of 4. And I then ask the question, if X is greater than Y, I want it to tell me a message. The value of X is whatever X is, which is greater than the value of Y. Okay, so I have a nice also conditional message that's going to use the actual variables to report back what's going on. So if I was to run this in R, okay, we know that X is 10, so that is greater than 4, and so it messages it back, it evaluates correctly. Now, if I was to change Y to like 20 and run that same if statement again, I get no message. Okay, because the logic is not met. You're not meeting the logic, it doesn't get to the message part. Okay. Okay, and so then getting a bit more fancy with this, we have the second part of an if else, the else. Okay, and so we can ask the question, if something applies, do this, else do something else. Okay, and so the way this is structured is we keep using the curly brackets and we sandwich the else in the curly brackets. Okay, and so we can then ask the question, if this is evaluated, if this is true, then it's going to do this first section that's between the first set of curly brackets. Else, it's going to do this second message. Okay, and so the messages we have is just a simple readout of just what's happening. So in this case, we're saying X is equal to 3. And so then it's messaging out 3 is less than 5 because X is less than 5. So it's evaluating this first message. When we set X to 10, it's no longer less than 5. And so it satisfies the else part of the operation. And so then you get this message, which 10 is greater than or equal to 5. Okay. And so then the final part of if and else statements is when you want to keep this branch going. Okay, maybe you don't have a simple yes or no, but you have multiple options that you want to test for. And so that's when we use an else if. Okay, so we start off with if in exactly the same way. If this condition is met, I want to do this first message. Else space if, And then you add a second conditional logical operation that you want to test for. Then you reopen the curly parentheses or curly brackets, and then you do a second test, okay? And then you can do this, you can reiterate this as many times as you want. You can have as many else ifs as conditions can apply in your situation. And then you finish it all at the end with an else, okay? Or not. If you don't want an else at the end, you don't have to. It all depends on your setup. But what we're doing here is, if it meets the first one, x is greater than 5, then it's testing, does x equal 5? And if it's not greater than 5, or if it's not doesn't equal 5, it's going to be less than 5, right? We're not testing that if it's less than 5, but by logic, it has to be. And we're adding that final message into the else, right? And so in this case, we run it and 5 as x equals 5. And so we evaluate this part here. And so we get this statement of 5 is 5. Okay. So this is really like fundamental in a lot of like when you start to work on scripts and you want to automate things and you want things to only evaluate under certain circumstances. And the more you start to work with these kind of statements yourself, the more use you'll see for them. But when it actually comes to the data side, when you're not controlling workflows, most of the time you're going to be actually using, or this function is more useful. And so this is the if-else function. Okay? It works in exactly the same way, but instead of you giving it like you having this kind of one evaluation, right, giving it like you having a message or something like that. And this allows you to create a vector in response. And so you can provide a vector, you can test a logical operation on that vector, and then you can get a response that is a vector of responses. And so, for example, here we've got x 1 through 10. Okay, something we've done a bunch of times already. We've assigned 1 through 10 to x. We then use if else. We ask, is x less than or greater, less than or equal to 3? If this is true, it's going to return the value less or equal. And if it is false, it will return the value more. And so this is a way of generating these categories based on something like a numeric, right? And so you can see the first 3 are considered to be less than or equal to 3, right? Because it's 1, 2, and 3. And then everything above that is considered to be more. Now, if you imagine our expression data, for example, if you wanted to turn your numbers of, I think it was running from somewhere like 19 up to 70, if you wanted to break that into categories, and add that as a column to your data, you could say, I want to know everything that's above 50, right? You can say, and everything above 50 is we're going to be considered to be expressed. Everything below 50 is considered background. You could then create a vector that says, is expressed less than or equal to 50? And then if it's true, it will be considered background because it's less than 50. And if it's false, it will be considered to be expressed. Right? And so this is a nice way of being able to categorize your data quickly. And again, it's a nice way to just add more information into your data frames. Okay. As with the previous if-else statements, these can also be nested as well. So if you want to ask something really complicated, you can put an if-else within an if-else. Okay, so if something is false, it will then evaluate a new if-else. And I've seen some really horrible code where people have taken this way too far. Like sometimes it gets to a point where there's better ways to deal with it, but this works and it functions and it's pretty like, once you get a hang of it, it's pretty straightforward to figure out this kind of like series of steps. Okay. Okay. So loops, how are we doing for time? Okay, we're doing okay. So the main kind of loop that people use is a for loop. And so for loops means you're going to execute a piece of code a certain number of times, given whatever your parameters are. And so a lot of the structure is very similar to an if-else structure, okay? We have our for statement. We have our conditions that we're evaluating based on. And then we have the code that we want to evaluate, okay? So the code we want to evaluate, again, it's in the curly brackets, while the conditions are in the parentheses, okay? But this time, the conditions are, I want to do it this many times based on this range, okay? So the range we're using in this example is 1 through 5, okay? And then the I is going to be the placeholder. So what I mean by this is every time it iterates through your code, I is going to be used within that code, and it's going to be the value of X for the number of times it's racing through. So the first time, the value of X is going to be 1, which means the value of I is going to be 1. Okay. Second time through, it's going to be 2, and so I is going to be 2. Okay. And so every time it goes through, it's going to message, in this case, the value of I. Okay. And so the way this is set up is you go I in X. But you can set this up in a variety of other ways as well, which we'll get into. Yeah, and so in this first example, right, we have 1 through 5, it loops through 5 times, it evaluates the code 5 times. It's going to evaluate the code considering X to be each of the independent values within X. And so this is the numeric example, but we also have here a character example. Okay, so again, here we have letters. So actually, I'll show you letters. So letters is a variable that comes with R, and it contains all the letters of the alphabet. So this can be useful sometimes. There's also one that's caps letters, and it's capitalized. Okay, so that's what we're using there. And in this case, I'm just grabbing the first 5. So that's what X is, A, B, C, D, E, okay? And so then when I run this for loop, it's going to be running through each time and doing that each time. I can also message. So this part here is just playing with the formatting a little bit so that they appear next to each other. If I do it like this, oh no, I've used 2. Then they appear one after each other. Okay, so that kind of illustrates the fact it's going through, it's doing A first, doing B next. It's very procedural, okay? And so this is actually one of the drawbacks of for loops. Because it is if you're doing something very computationally intensive, it can take a while because it's not parallelized at all. So when we get to advanced bioinformatics processes that take a while, you want to be running multiple processes at once so that it's quick. But if you do a for loop, it's going to be doing once, then it will finish, then it will do the second time, then it will finish, then it will do the third time. And so it can be quite slow. Sometimes it's what you need, but sometimes it's not.
Okay, now there, please.
Pardon?
Okay, now there.
Okay, yeah. So that's this, and what this does is when it messages, it prevents it from basically starting a new line. And so this is mostly for the interest of keeping everything on one slide. But if you saw here, when I just deleted append LF here, it puts it onto a new line each time. Okay, so in message, there's a lot of ways you can control messaging and things like that. Again, generally you won't be using for loops for messaging really, but this is like a nice demo. Messaging is really important when you start to build your own workflows and scripts and things like that, so you know how your script is doing. So then you can play with all the formatting options then. And so how does this kind of for loop work in practicality? This is the way I often use them if I use them, is say I have say I have these values, right? Instead of providing 1 through 5 or something like that, I will say 1 through the length of whatever object I'm working on. So in this case, I have this length that's gene name, right? It's 3 long. Okay, it's 3 long, there's 3 genes in it, okay? And so I want to perform something on each of these genes. And so I'm going to iterate through them. Okay, so what I'm doing here is I'm saying for every instance in my 1 to the length, so basically 1 to 3, I'm going to message out the gene name. Okay, and so I'm using the I to index at this point. Okay, so this is, I think, the most important way to use this is actually you're using your iterator as an index to be able to control dragging out different pieces of information from objects you come into it. So in this case, I'm getting information from the expression data set, right, and I'm getting information from the gene name. Okay, and we know the value of I is 3 at this point because it's run through once, so I is left over as 3. Okay. So what you can do with things like this is you can build something quite complicated where maybe you want to actually run some tests and you iterate through every single option, and then it only messages you if something happens. So you can set up this for loop that's going to for loop over a big data frame, and then it will send you a message if something's true or if something evaluates or whatever, something like that. Just like I was saying here. Yeah, so you're doing a for loop and you're saying I have 1 through 13. And so you do this loop and then you're asking the question, is I greater than 10? So the first time it's like, no, it's less than 10, it's not less than 10, it keeps going, and it is 10, then it's greater than. So combining these different things can help a lot build these kind of complex arguments and complex logical structures to answer the questions you have. Now, as great as for loops are, most of the time what I do instead of doing a for loop is I use a group of functions called apply. And so why apply is better is it's a kind of vectorized way of approaching that problem. And so instead of going through 1 by 1, I'm asking the question multiple times at once. And as a result, the mathematics is a bit faster and it runs a little bit faster. Also, the nice thing about applies is they typically return a sensible object for your question. And so I'll show you this in action in a sec, but it will show you, it will run through, and depending on the type of apply you use and the question you're asking within your apply loop, it will give you something back that's much more sensible than like things that are printed to a screen or creating your own data frame on the fly, which is quite hard to do in a for loop. And so there's multiple kinds of apply. The three most used are apply, lapply, and sapply. I'm only going to tell you today about sapply, okay? Because sapply is the smart apply. It tries to do the best thing that it thinks that you want to do depending on the inputs and the evaluation, okay? lapply is designed for lists, okay? And it always returns a list. So you put a list in, you get a list out. Regular apply is designed for matrices and data frames, and it goes row by row, okay? Or it goes column by column. Both of them are really great, but sapply can be generalized to work in both ways. So in this case, I have an example vector, an example list, okay? They both contain the same information. And what I'm asking you to do is go through each entry and do the mean function on it, okay? So the first argument is similar in a for loop to the for I in 1, 2, whatever. Okay, instead, you just give it a vector of some kind, in this case, 1 through 5. The second argument is whatever function you want it to do. Okay. And then after that, you can apply any arguments for that function. And so in this case, this is actually, I'm realizing now it's a pretty bad example because what it's doing is it's going through and it's doing mean on single numbers. And so it's going to the number 1 and it's doing mean on 1 and it's returning 1. Then it's going to number 2 and doing mean of 2 and that's 2. And so it's going through like that. But what it's realizing is that no matter the input, it's a vector, it's a list, no matter the input, it realizes that what you're getting out is basically a vector of 1, 2, 3, 4, 5. And it's giving you that. Now, if we do something a little bit more complicated, and so we could use this function called the quantile function. And what the quantile function does is it breaks things up into, basically, it does what it says. It breaks things up into quantiles, okay? And so what this sapply is going to do, or this lapply, is it's going to apply quantile to this list. And so this list has 3 different entries. There's 1 through 5, 6 through 10, and 11 to 15. So the way this is working is it's going to go to row 1 here, and it's going to apply quantile. And then it's going to go to row 2, apply quantile, and go to 3 and apply quantile. And so if you do this with lapply, what it returns, because it's lapply, is going to return a list. And so what you get here is quantile, the 0%, the 25%, 50%, the 75%, and the 100% is 1, 2, 3, 4, 5. The 0%, 25% in row 2 is 6, 7, 8, 9, 10. Okay, but it's returned it as this list. However, if you do sapply, it returns it as this data frame, which is much more easier to use, and it's probably going to be more practical going forward. Okay, but I think though I've kind of started to show you these differences between sapply and lapply, what I really want you to take from this is all we're doing here is providing a list with multiple entries, and we provide a function. And what it's going to do is go through every single entry and apply that function to it, and then return it in a kind of sensible format. So you could be doing some kind of mathematical operation or all kinds of different statistical tests, and you do apply, and you do it to every single entry in your list. You can do it to every single entry in your data frame, things like that. Okay. And then, yeah, in this example here, we're doing, we have this example list, which contains a multitude of different things. We have a data frame, some data, and a vector. And we're applying the function summary, and summary does different things depending on the result. And because it can't simplify it down, all these different results look different. And so it can't make a matrix from it. It can't make a data frame. It can't make a vector. So because they all look different, so it returns to just using a list, okay? Because the list makes sense for this output. And so sapply, it's called smart apply for a reason. It tries to do the simplest kind of result for you. Okay, nearly there. So we just have like 3 slides on plotting, and then we're going to, or 3 or 4 slides on plotting, and then we're going to be done. Okay. So something we've talked about is this concept of base. Okay. And some of you may have heard of ggplot. Okay. So I'll show you why ggplot is great later, but plot, which is the base plot, does a pretty good job. And it's also similar to sapply, it is smart. Okay, so depending on your inputs, it will do a plot depending on what you think it thinks you want. So in this case, I have this data frame, which is our merge data frame. I can show you what that looks like. Just from the merge. So this is our merge data frame, right? We have some numbers at the end of length, expression. We have some pathway information. And so these are basically categorical data, some characters, and some numbers at the end, right? And so what I'm going to do here is I take the data frame and I provide it the final 2 columns. And this is unfortunately cut off. But what we have at the bottom on the x-axis is expression. Okay, so what it's done is it's realized, hey, these are 2 numbers. Why don't I plot them against each other? Okay, and in this case, in this data set, there's no correlation between length and expression. But a lot of the time, you see this kind of correlation between length of a gene and expression, right? But you can see how quickly we can go from a big table to actually having some data set. Now we can try something different. We can try with a factor. Oh no, this one. As I mentioned before, many plots like factors. Okay, there's a reason we use factors. I mean, if you remember when we looked at the summary function, we get much more informative information about your data if we have it in a factor format. And so in this column here, at the moment, it's just a character. Okay, this contains the information about whether it's a glycolytic pathway or a TGF-beta pathway. Okay, all it is says glycolysis or TGF-beta, right? And if we provide this to plot, it gets confused, it doesn't know what to do, it gets upset. But if we turn it into a factor first and then plot, it will just plot you a nice bar plot. Okay, comparing the 2. And then there are also some specialist functions which aren't just plots. There's a lot of different functions for plotting. But so this is an example of, we took the box plots function, and you tell it, I want to look at the expression levels as a function of the pathway. Okay, so it splits up into the pathway, the 2 pathways, and then you say, this is the data set that's coming into this. Okay, and so then you can do a box plot nice and easy. That said, ggplot is, this plot is great if you're just starting out, or if you are just looking at your data for the first time and want a quick result. But if you're starting to produce stuff that you want to go into a presentation, or if you want to go produce stuff that's going to go into a paper, it's very straightforward to use ggplot to then start to build something that's much more complicated and nuanced. And so this is the same data, but I've got a violin plot laid over a jitter plot. I've got some nice colors and themes set up for it. And it's only a couple more lines than what we had before. Yeah, and as you get started with plotting, I'm just going to recommend one specific resource, and that's the R graph gallery. And so the really nice thing about this is, say you go to violin. This has a bunch of different examples of plots, both in base R and in ggplot. And it has all the code. So you can get your data frame to look like their data frame, and then get their code to make a plot that looks similar to what they did, except it's your data. So it's a really, I need to go back. It's a really good resource. Oh, there we go. Okay. So we also have courses on ggplot as well. They're on YouTube, they're on their thing, and we'll probably, this is one of the ones I'm thinking about running in the new year as well. So hopefully I'll see some of you there for that. There are some exercises if people want to stay around. Just to clarify what we didn't cover, if you do want to get deeper into R, we didn't cover matrices, I mentioned that. We didn't cover while loops. We didn't cover coercing data types. So that's if you say you have a data frame and you want it to be a vector, or you want it to be a list, there's ways to force it, okay? We also didn't cover creating your own custom functions. This is where you can start to do really powerful things. Once, if you realize you're doing something repeatedly, you can create a function that allows you to do that much quicker rather than recoding it or copying and pasting code. And then we didn't cover actually making scripts which will accept an argument and run a workflow for you. But again, we touch on all of these things in our larger course. And if you want to kind of talk about that, you can talk to us, okay? And so if you need further help, you can go to our GitHub, especially if it's pertaining to this specific course or other courses we have online. Go to the associated GitHub, raise an issue, and I keep an eye on things. And so if something's not working, you have a bug, your computer's not working right, you're having installation issues, you can let me know that. You can come and talk to us, as in email us or drop by our offices. So our email is brc@rockefeller.edu, and we can help you with any of your analysis if you're stuck. And then there's other website resources like Stack Overflow and R Help. So R Help is specific for R, but Stack Overflow is anything coding based. And also just Google. Google is the most important resource for anybody coding. So that's always a good place to start. Cool, so that is all I've got to present. There are exercises if anyone wants to stick around, but I know it's also been pretty tiring a lot, and people's brains must be a bit tired. So I'm not expecting anyone to stick around, but I will be around, okay? If anyone has questions or needs further help with installation stuff, they can also grab me on their way out as well. Okay, everyone good? Nice. Thanks also for coming as well.
Okay, I'm just going to quickly run through the answers to the final exercise. And so this focuses on the steps we talked about with conditions and loops and filtering and things like that. So first off, we need to read in some data. So this is similar to all the data we've read in so far. It is present within the data directory here of the downloaded course material. And it's specifically a text file called categories and expression.txt. And so then to read it in, you just need to do read.table. And it is specifically a tab delimited file. So we covered earlier comma separated files. This is separated by a tab. And so sorry. It's a tab separated file. So you have to provide this information for tab separation. So that's a \t. And so you can see what it looks like when we read it in. Gene name, it's selected glycolysis expression. So this is basically the same one we've been looking at. But it's yeah. And so what we're going to do in the next part is filter it to the of interest column to just the selected. Okay, and so you can see that the of interest column has either selected or I think it's unselected as an option, but we want to just get the selected. So we can use the double equal sign as our logical, and we say I want the interest of interest to equal selected like this. And then you can filter it. And of course, we're filtering by row because we're filtering out by gene. Okay, so we leave the column empty and we put this into the row file. And cool. So we have this. So next, we want to take this subset data frame and we want to reorder the subset from the smallest to the largest in gene expression. And so this is going to be just simply using the order function. And because we want it to go from smallest to largest, we don't even have to concern ourselves with the additional argument decreased. So it won't be decreased equals true. It's just going to be order on the expression and then re-index based on this. Okay, and this provides us with the result, which is my DF subset ordered. Great. So the next exercise is going to be about a for loop. And so we want to calculate the factorial of 10 using our loop. Okay, so this is just getting people to set up loops correctly, see if you can get a loop going okay. And so within this, if we want to do basically 10 times 9 times 8 times 7 times 6, we want to do it iteratively by using a for loop. And so what we need to be able to do is do for x in 1 to 10, right? So because we want to go through this 10 times. The next step is actually the first time we do this, when we go to x equals 1, we don't do any multiplication at this step. We just need to produce the number 1, right? And so what we're going to do here is we're going to do x, if x equals 1, so double equal sign, we want to do this. We want to assign our answer to this variable called factorial answer. Okay, and we're going to just assign the number 1. Okay, and so in the first time it goes through this for loop, it's going to evaluate this, and the factorial answer will be assigned by 1. Then, when it's above 1, so when this is no longer true, it evaluates to else, and it's going to multiply factorial answer by x. Okay, so the first time this goes through, it's going to go factorial answer equals 1. The next time, it's going to be like, oh, this isn't true. It's going to do this. And so it's going to be, let's multiply 1, which is here, by 2, which is our x. And then it's going to overwrite the variable factorial answer to update it to the value of 2. Then it's going to go through again. I'm just going to go through this just a little bit, just so that it's clear. X is still not 1, so it's going to get to this bit. And factorial answer at this point is equal to 2. X at this point is equal to 3. So it's going to do 3 times 2. And then it's going to reassign factorial answer, right? So if we think about that, we have essentially evaluated this at this point. We've got 1, 2, 3. And at this point, our factorial answer should equal 6. When you continue this on, you get up to 10, you end up with actually quite a large number. Okay, using the if-else expression, create a factor from the vector of 1 to 40, where all numbers less than 10 are small, 10 to 30 are mid, 31 to 40 are big. So this is the if-else function that we talked about. It's a really nice way of striating your numeric data into categories. And so we have multiple levels within this if-else, right? Because we don't just want an if and an else. So that means we're going to have to nest our if-elses. So we're going to do if else. We're going to ask a statement. Is the value less than 10? If so, it's going to return small. If that isn't less than 10, you get to ask it a second question. Is it less than 31? If that's true, it's mid. And if it's not less than 31, at this point, it would be considered big. Okay. This would result in our vector result. We can then also create a factor from it. So we're creating a factor. So we do factor on the result. The levels are small, mid, and big. So these are the options. And we're actually providing it so that they're ordered. Okay. Because if we didn't provide the levels, then it would be big, then mid, then small, and that would be the order of things because it defaults to alphabet. And then because these are ordinal, small is smaller than mid, which is smaller than big, we can actually say order equals true. And so you can see here, we have all these values of small, mid, and big, corresponding to less than 10, 10 to 30, and 31 to 40. And the levels are ordinal, because you can see that the small is less than mid, etc. Lastly, we have exercise 3. And so this is actually a pretty nuanced question and a little bit tough. But I'd be impressed if you get here, you work through it, it shows that you've got a good grip of everything. But that said, if you're struggling, also don't beat yourself up. It's quite challenging. So read in all the files from expression results with the .text extension using sapply and create a table of gene expression results. So I provide a note saying that the directory function can return only specific file types with the pattern argument. Okay, so we've met the directory function a couple of times. And so what we do is a directory, say directory, and then we point to the expression results folder. So again, this is assuming you've downloaded the course content and you've navigated to the R course folder within it. And if not, you can point towards it. But what we're then asking is that this ends in .text. Okay. So this pattern information, I think, considering you could probably be able to delete this. But this implies that what we're expecting is it to be the file extension. But I'm pretty sure .text will be the end of any of these files anyway. But we're providing this additional argument. It's basically a pattern that says it has to have .text in it. Okay, and if let's see here. Yeah. So if I do this, you can see there's these .text files here. And so those are the ones we're going to be reading in. So we now have a vector that contains all the files that we want to read in, and their names and their paths to them. And so now if we're going to read in a bunch of files, what we want to do is use some of these tools that we've learned to be able to read them in. And so if you look at these files, they are separated with, again, the tab separated, and they don't have a header. Okay, so no column header. So what we can do is we can use sapply, and we're saying we're going to do sapply on every single entry within this vector. Okay, and we're going to do read.len. So we're providing all the paths to these files, and we're going to do read.lim, and these are the arguments we want to use for read.lim. And so this means we're going to end up with a list that contains all the data frames that we just read it. Okay, let's switch to RStudio so you can see this. Oh, I missed the F. Let's just do this. Okay, so fast to read looks like this. Bunch of files, and then files read could be this. Okay, so it's a list with all these different entries. So we can check how long it is. It's a list, length. Nice. Cool. Great. And so once they're all read in, let's switch to here. Okay. Now we can use a for loop to merge everything. So what this for loop does is it iterates through our merge table, where it asks, basically we set up a merge table to start with. This is my merge table. Okay. We ask in file read. So it's going to iterate through each of these files, each of the slots within our list. And it's going to say if this is still null, it's going to say merge table is the first entry. Okay. And then every subsequent one, it's going to merge the merge table to itself, to the entry. And so the reason we're doing this in our for loop is if you consider if in our for loop we're going through our list, right? If you get the first one, it cannot merge to anything because you don't have a second one, right? So what we're doing is we set up with this null. If it is still not, if it's null, which only happens for the first entry, it's overwritten by the first entry within the list. Then when we get to the second entry, you're able to go, oh, merge table is not null. So let's merge table with our second entry, merge it. Okay. Then we'll go to the third point. Our merge table has been updated, so it now contains the information from both slot 1 and 2 in our list, and we're going to add slot 3. Okay. And then we have this little timer here. So every time it iterates through, it's going to print us the row of the table. But yeah, so we end up here with all this count information that's been attached. So if we remember, this object had a bunch of different count information. Then we're going to add the annotation information from here and merge it in as well. Okay, it's a similar operation, it's just another merge. And then we ask the question, how many of each pathway are in the table? Can you also show this information with a plot? Okay, so what we want to do is use our knowledge of factor to do factor on the pathway. So once it's factorized, we can do summary. Okay, and summary gives us a summarization of how many existing pathways there are. Some might not have a pathway associated with them, so they're NAs, but we have this many of each of the others. And then we can just simply run plot on this, and it tells us how many exist of each. Okay, so that is the exercises. Thank you for sticking around. and reach out to us if you have any help, need any help. Just reach out on GitHub. See you soon. Bye.